Hi, Dr. Tashawn here, and in this video we're going to evaluate limits that involve complex fractions. Let's talk about what a limit is before we do the examples. A limit that you would study in a calculus class tells us where a function is going. As your x values approach a number from the left to the right, tells us where the y's are going. Here is the notation on the board. The limit as x approaches a value from the left to the right of a function equals, and we have to figure out how to figure out where the y values are going. So how would we approach this in an analytical sense? Over here on the screen, I put together a flow chart that helps us determine how to analytically go through and evaluate limits. So just a quick review. Anytime you have a limit problem, and we're not looking at a graph or a table now, we're doing this analytically, algebraically today. So if you have a limit problem, then the first thing you want to do is you want to utilize the direct substitution principle. We want to take the c value where the x's are going, and substitute it right into the function. So one of three things here will happen. You will either get a real number, no zeros in the denominator, so that is your answer. Or you might get a zero in the denominator. Now, zero in the denominator comes in these other two forms. You can have 0 over 0, indeterminate form, or a non-zero over 0, which is undefined. These two situations are handled differently when you're evaluating using limits. In this video, we are going to look at the 0 over 0, and we're going to deal with a complex fraction. So there's complex fractions involved with a 0 over 0 strategy is what we're going to look at here. So let's take a look at the examples that are on the board. We'll do these two examples. Example number 1. So let's come on over here and let's take a look at example number 1. Let's take the limit as x approaches -2, and we have 1 over x plus 1/2, and in the denominator we have x plus 2. So let's take a look at this example. First thing we want to do when we're evaluating limits, it's a limit problem, and we're going to evaluate this algebraically, is we want to utilize the direct substitution principle. We want to take the c value, which is -2 for this example, and we want to substitute it into the function so we can see what approach to take. This can be done mentally, or I'll write it out and erase it in just a minute, but let's just go ahead and see what we're dealing with here. So we're going to take the -2 and substitute it in for x and compute. So in the numerator of that fraction here, we have 1 over, we're going to substitute -2 in for x, plus the other fraction is 1/2. In the denominator, substitute -2 in for x, and we're adding 2 to that. So when you compute the numerator, -1/2 and +1/2 gives you 0. The denominator, -2 and +2 gives you 0. So this here with direct substitution yields indeterminate form. So indeterminate form, so what does that mean? Well, this function, as the x's approach, whatever the function is going to look like, all right, as the x values approach -2 from the left and from the right, as the x values approach -2 from the left and from the right, we want to figure out where the y's are going. Because you have indeterminate form, this graph has a hole in it when x is approaching -2 from the left and the right. So this function here is not defined at x equals -2. However, the left and the right are going the same place. On the y-axis, they're going the same place. And I just drew this arbitrarily. We don't know where it's going yet, but it is going the same place, and we are going to figure out where it's going. So how do we figure that out? Well, so we know this is a 0 over 0, so we need to take the function here, and we need to change the form of the function. We need to change the form and simplify. We don't want to do anything more with the function. We just want to change the form. So what can we do here to change the form of our function? Well, it's a complex fraction. You have fractions inside fractions, and let's simplify the complex fraction. There's a couple of methods that you can use in simplifying complex fractions, and I showed you a couple of methods in a different video if you wanted to go and take a look at that for the algebra review. But we're going to go ahead and just simplify the complex fraction. So take a look at this, and what we want to do in here is we want to look at the fractions within fractions and take their denominator. So x plus 2 down here is okay, but 1 over x, 1 over 2. Let's look here, and so we want to figure out with our fractions within fractions, what is the least common multiple that I can multiply top and bottom by, so that's going to clear out the fractions. So this term is okay, this term is okay. Here we've got the x and here we've got the 2. So let's multiply by the 2, let's multiply by the x. Same thing with the denominator, let's multiply by 2, multiply by x. We're going to multiply this whole fraction top and bottom by 2x over 2x. Now if you reduce 2x over 2x, you're going to get 1, aren't you? So 1 times this fraction gives us the fraction back. We're not changing the value of it, just changing the form so we can come up with the limit. So let's go ahead and write this down. So we have the limit, and x's are approaching -2. All right, in the numerator, we want to distribute. Okay, so distribute, so 2x multiplied by the 1 over x, and we want to take the 2x multiplied by the 1/2. When you distribute 2x times the 1 over x, your x's cancel and you have 2. When you distribute 2x to the 1/2, the 2's cancel, you have x. So here's what we get when we distribute it in the numerator. So distribute, here the x's cancel, bring down your operation sign, and then distribute, the 2's cancel here. The denominator, let's leave the denominator in factored form. Don't multiply this out, let's leave the x plus 2 multiplied by the 2x. Okay, well why would we do that? Take a look, can you see why we would do that? Because we have a common term, we have 2 plus x in the numerator, x plus 2 in the denominator. We can go ahead and cancel those because addition, the operation of addition is commutative. So 2 plus a number plus 2, either way you add them, you're going to get the same thing. So essentially these factors are the same. You can go ahead and cancel the x plus 2's. So let's see what we have now. So we've taken the limit as x approaches -2. Right, our numerator, because we canceled out the x plus 2, 2 plus x factors, we just have a 1 in the numerator. Denominator, all we have left is the 2x. All right, and then finally, so we took our complex fraction, we completely simplified it, and then you take the completely simplified form, now take the -2 and substitute it in. When you substitute it in, you can lose the limit notation. We have a 1 in the numerator, and then you have 2 times -2 in the denominator. Substitute in the -2, just direct substitution. We can reduce, not reduce, but we can actually go ahead and compute this to be -1/4, and here is your answer. This is what the limit of this particular function is that contains a complex fraction. So now what does this tell us? Okay, so on this function, we took the -2, we substituted it in, and we had indeterminate form. So what does that tell us about this function? This function is not defined at x equals -2. It's not defined at that point. However, as the x's approach -2 on your graph from the left and from the right, where are the y's going? The y's are going to a -1/4. We're able to compute the limit. We just have to do some algebra. If you have a complex fraction involved, just simplify it. All right, let's take a look at example number 2. Same idea. Okay, same idea. This is a limit problem. So this is a limit problem right here. So how do we evaluate a limit problem without using a table, without using a graph? How do we evaluate a limit problem analytically? Okay, so take a look at the flow chart. Flow chart will help you with going through the process. So it's a limit problem. Let's use the direct substitution principle. Direct substitution principle says you're going to take the c value and substitute it in. Substitute it in so we can see what kind of work we need to do. So I'm going to do this off to the side, and then to substitute the c value in. Could be mental math, you could just do this in your head, but plug it in. So you end up with in the numerator, when you plug in 0 for x, we're going to have 1/3 minus, and then this 1/3 here. The denominator, substitute 0 in for x, and we're here. When you combine the terms in the numerator, you're going to have a 0 in the numerator, a 0 in the denominator. This is indeterminate form. What does this mean that we have indeterminate form? Well, first of all, when you take 0, okay, as x's approach 0, x equals 0 on this function's not defined at x equals 0. Because it produces indeterminate form, this function, you have a hole in the graph. You have just a hole in the graph, so you will have a limit. As the x's approach 0 from the left and the right, the y's are going someplace. The y's are going someplace. We've got to figure out where they're going. Because you have indeterminate form, because there's indeterminate form, we need to take this function and change the form of the function so we can find the answer. So what strategies do you use? In the flow chart, and I have other videos out there, so you look at the function. If you have polynomials that can be factored, then you can utilize the factor and cancel method. Right? If you have radicals involved, you might be able to multiply by a conjugate. Okay? We have complex fractions here, so we can simplify the complex fraction. All right. There's other techniques to use for the different algebraic expressions. So let's simplify this complex fraction. So we're going to take the numerator and the denominator, multiply every single term by the least common multiple of the numerator denominator. We're going to multiply by the least common multiple. This method here of multiplying top and bottom by the least common multiple it's the quicker method. You can go ahead and simplify complex fractions in one step when you do this way. So x in the denominator is okay, but look at the numerator. What do we need to multiply by? We've got the 3 to get rid of, and the 3 plus x. Okay? So, and whatever we multiply top by, we have to multiply the bottom by the same thing. All right? So we have to multiply top and bottom of this fraction by 3 times the quantity 3 plus x. Make sure multiply the top and the bottom so you're not changing the value of this function. Okay? So 3 times 3 plus x over 3 quantity 3 plus x. When you can't, these reduce out to be 1. 1 times this fraction gives you the fraction back. So it's what we want to do here. So what do we have? So we have the limit. X is going to 0. We want to, in the numerator, distribute to each of these terms, right? When you take this expression and distribute to this term, the 3 plus x's cancel, so you have a 3 left over. Bring down the operation sign. Bring down the operation sign. Now let's distribute this expression over to this term. Here the 3's cancel. The 3's cancel, but be careful, the 3 plus x that's left over, make sure that you retain the grouping symbols for it as well, because subtraction sign is going to have to be distributed. What about our denominator? Well, denominator you have x, and we have 3, and we have 3 plus x. All right, so we have this in the denominator. Leave your denominator in factored form, but your numerator, you want to expand your numerator. Okay? Next, let's simplify this numerator. Simplify. You're going to have to distribute that negative sign. These are the algebraic steps to work through next. So distribute the negative sign. You have the limit. X approaches 0. So in the numerator, you have 3 minus 3. Okay? And then minus x. There's your numerator. And your denominator, we have x. And we have 3. And we have 3 plus x. Don't multiply the denominator out. Leave it in factored form because you're going to be able to cancel common terms. Now notice in the numerator the 3's cancel. So we can cancel 3 minus 3 is 0. That's going to go away. So when we simplify further here, we have the limit. X is going to 0. When you cancel the 3's, 3 minus 3 is 0. Notice we have a negative x in the numerator. Denominator, we have an x. We have the 3. And we have the 3 plus x. All right, can we simplify further? Yes, the x's cancel, and we need to move those x's out of the way. So you're going to need to cancel whatever strategy you're going to use, factor and cancel. Multiply by conjugate and cancel. Simplify complex fraction and then cancel common factors. So you need to cancel because you're canceling out the 0 over 0. You got to make that 0 over 0 go away. So you cancel, so negative x over x. Okay, so well, let's see. So you can cancel, and the numerator gives you a negative 1 over 1. The x is canceled, but notice that you still have the negative left over in the numerator. All right, so we go ahead, we've got the limit. As x approaches 0, what do we have in the numerator? Well, negative 1, because the x is canceled, but we still retain the negative. What do we have left over in the denominator? We have 3, and we have 3 plus x, okay? The x is canceled, so we have these two left over, okay? All right, and now let's compute the limit. Compute the limit means you're going to take the 0 now and substitute it in. That's how we compute limits. You take the c value, you substitute it in. If you get 0 over 0, then you have to algebraically change the function, and then you do the same thing, take the c value, plug it in. So we take the c value, plug it in. We have negative 1 in the numerator. The denominator, we have 3. And it's multiplied by 3 plus we substitute 0 in for the x, okay? And then when you multiply this out, we have the -1 in the numerator. 3 times 3 gives us 9 in the denominator, -1,9. Here is the answer to this limit problem, okay? So here's the answer to the limit problem. So information, it gives you information about what the graph of this might look like. We know that at x equals 0, this function is not defined. At x equals 0, this function is not defined at that point. However, as you approach x equals 0 from the left and from the right, the y's are going to -1/9. This tells us where the graph is going when you don't have the table and graph to actually look at. So this is the algebraic method of getting through and evaluating limits when you're going to simplify complex fractions. Okay, that's it for this video. So thank you so much for watching. Appreciate it, and thank you. Bye-bye.